This is Jack Jackson. In this video we're going to talk about some general characteristics of certain types of trigonometric functions, and we're going to analyze at least one trigonometric function in some detail. And we're going to be using things from algebra and from trigonometry to analyze these, but also some calculus as well. The first thing you need to know is when working with trigonometric functions in calculus, always put your calculator or computer program in radian mode. Throughout, we will assume that we're using radian mode, and the shortcut rules that we have determined for derivatives basically are assuming that the input is in radians. Now, trigonometric functions have some similarities to things like polynomial and rational functions. And like rational functions, the 6 basic trigonometric functions are differentiable everywhere they're defined. Now, the sine and cosine functions are defined everywhere, so they're a lot like polynomial functions. They're going to be one continuous piece. In fact, they're not only defined everywhere, they're differentiable everywhere. So like polynomials, sine and cosine functions are one connected, smooth piece. But like some rational functions, tangent, cotangent, secant, and cosecant have places where they're undefined and have vertical asymptotes. In fact, tangent, cotangent, secant, and cosecant actually have infinitely many places where they are undefined, and at each of these places they will have a vertical asymptote. Now, unlike rational functions, the basic trigonometric functions are periodic. That's one of the main things about them. In fact, one of the main reasons why we study trigonometric functions is to study periodic behavior, or to apply them to periodic behavior. So anytime you have something that goes in a cycle, whether that's the number of hours of daylight on a particular 24-hour period, or whether that is seasonal sales of some item, whatever it might be, anything that comes in a cycle, or waves also come in cycles, anything like that that has a cycle to it is going to be periodic in nature, and we can use trigonometric functions then to model them in many cases, model these real-world phenomena with periodic behavior. So, for example, if a function has one x-intercept and it's a trigonometric function, then guess what? It's going to have infinitely many x-intercepts. If it has one maximum, it's going to have infinitely many maxima. If it has one vertical asymptote, then it has infinitely many vertical asymptotes, etc. And so, one of the most important things to do when you're analyzing trigonometric graphs and trigonometric functions is that you take account of this periodic nature. So you're not going to be able to find, say, just 1 or 2 or 3 x-intercepts, but these infinite classes of x-intercepts. Now, the first thing you need to know when you're going into calculus is, of course, that it has a prerequisite. And the prerequisite is that you know some arithmetic, some basic geometry, some algebra through college algebra, that is through Algebra 1, Algebra 2 in high school, and maybe a little beyond that, into pre-calculus or Algebra 3. But you also need to know some trigonometry. And so I assume going forward here that you know how the basics of trigonometric functions and trigonometric graphs. If for some reason your background is weak, either you skipped a trigonometry class, a good solid trigonometry class in high school, or you've forgotten some of it, or whatever reason that you're a little rusty or a little weak on your trigonometry, I refer you back to my trigonometry videos. So I have a playlist called Trigonometry Unit 2 that's circular trigonometry, and it introduces the definitions of the 6 circular trigonometric functions and visualizes these both on a unit circle and via Cartesian coordinate graphs. Okay, and they also have some videos there in that playlist going over trigonometric values for certain special angles. They're special only because, not because they're particularly important, but because they are easy to figure out exact values as an algebraic expression, as a number, maybe with some radicals in it, but as a specific number rather than, say, just as an inverse trig, and you have to leave it like that. And then I also refer you to my Unit 4 playlist for trigonometry, in which I talk about identities, equations, and inverses. And it's going to give some examples of solving equations, and it's going to build this up a little bit more slowly than I'm going to be able to do in this video. And in both of these cases, there are a number of videos within these units, and you can look at those videos to develop these concepts a little more carefully and slowly. So let's look at this example right here, and we're going to spend the rest of the video analyzing this particular one. So here is a particular function, f of x equals 2 sine cubed of 3x minus sine squared of 3x minus 2 sine of 3x plus 1. So there is a trigonometric function. It's not just a basic sine or cosine, but it's rather a composition, really, of you start by taking x and multiplying by 3, then you take the sine of that, and then you put that in a polynomial, a cubic polynomial function. So it's actually a composition of a cubic polynomial, a sine function, and a linear function. Okay, so what I want you to do is to analyze this completely. So we're going to find the first derivative and the second derivative. We're going to find out when this particular original graph has x-intercepts, y-intercepts, local extrema, inflection points, all the interesting things about it. Does it have any holes in the graph or vertical asymptotes? How about horizontal asymptotes? Do any of those apply? So we're going to answer all those questions. Some of the answers may be none in some of those cases, but we want to work through those carefully. Now this particular one is going to review a whole bunch of skills from mainly from trigonometry, but also some algebraic skills as well. So this is going to be a good review to see if you remember all these things from trigonometry. And once again, go back to those trigonometry playlists if you need some more help with that. So what we're going to do now is I'm going to ask you to pause the video here in just a second, work through this, see if you can figure out all those things that we just talked about. And then from there, we're going to go, and when you think you have it pretty well analyzed, then come back to the video and follow along with my solutions and see how you did. So press pause now. Okay, so notice if we do a substitution, u equals sine of 3x, this becomes 2u cubed minus u squared minus 2u plus 1. So that's a polynomial, third degree polynomial, or cubic polynomial. Now notice that sine of theta is periodic with period 2 pi, and if u is sine of 3x, that's going to be periodic with period 2 pi over 3. In general, when you do a transformation of a sine graph and you replace x by 3x here, or x times a constant, this coefficient here is going to be, well, if you take 2 pi divided by that coefficient, you will get the period. And so, of course, if you have, just think about it this way, another way to do it is if x is going from 0 to 2 pi is 1 period, multiply everything by 3, and x is going, then 3x goes from 0 to, I'm sorry, the 3x, when it, let me start that over again. 3x goes between 0 and 2 pi will be 1 period. So 0 is less than 3x is less than 2 pi. Divide everything by 3, and we get where x is in the middle, and we get 0 divided by 3 is 0, and 2 pi divided by 3 is the top. So x going from 0 to 2 pi over 3 is 1 period, And so the period in general is 2 pi over 3. And since this is the period of sine of 3x is 2 pi over 3, and this is just a function of that, then a function of that u, that's sine of 3x, it'll turn out that f of x is also periodic with that period of 2 pi over 3. So we're going to see that a little bit later on in more detail as we go through it. So what that means is, among other things, is if you graph the function from 0 to 2 pi over 3, you'll get a portion of the graph, and the rest of the graph is just horizontal shifts of that same piece over and over and over and over again, infinitely many copies of that. So let's summarize what we know so far. Well, what about the domain? You can multiply 3 by anything. That's going to be all reals there. You take the sine of anything and get a value. That's good. And you can do a polynomial of anything. So there's nothing in this that would kind of mess up. There's nothing that would cause division by 0. There's nothing where we get 0 to the 0 power, or any of the other things that might give us, square even root of a negative. None of that stuff comes up. So the domain here turns out to be all real numbers. And notice that y equals 3x is a continuous function, y equals sine of x is a continuous function, and y equals a polynomial is a continuous function. So when you compose these continuous functions, you get a continuous function. So in fact, it's continuous on all reals, and for more than that, it's actually infinitely differentiable on all reals. You can differentiate it. The first derivative is defined everywhere, the second derivative is defined everywhere, third derivative, fourth, fifth, sixth, seventh. Derivatives on forever are all defined. And the period should be 2 pi over 3. Now, one of the first things I might do is actually just graph this thing. So actually type this in more or less like it is on your calculator. The only thing you have to do on your calculator or in some computer programs is remember that it doesn't like this notation sine cubed of 3x, which is really kind of a shorthand notation really for parentheses, sine of parentheses 3x, close parentheses, then cube. And so you have to kind of put it in that way. And similarly for the square here. So if you put that in your calculator, or in this case in Graphmatica, here is a graph where we graph several things. I graphed it with a grid spacing of pi over 36 apart, and that actually works out to show some of the interesting places. But here we see from 0, and it goes up and down here, and up and down a little bit more here, and we're kind of back at the level we started at. That goes at whatever level this is at 0, comes to the same level here. That's going to be at 2 pi over 3, which is the period, right? 2 pi over 3, yeah. And so this piece here from 0 to 2 pi over 3 is just replicated again as we shift to the right or to the left. Now notice within one period here, you're going to have, it's going to cross the x-axis 4 times. It's going to have 2 maxima here. It's going to have a maximum right here where it touches the x-axis. And it's going to have minima here, and one right here where it touches the x-axis. And inflection points, let's see here, this is starting concave down here. Somewhere in here it switches to concave up. So there's an inflection point right in here somewhere. Concave up, switches to down. So right in here is another inflection point. Another one right here where it switches from down to up. Then we switches to up to down. Inflection point about here. Down to up is about here somewhere. Back to down is about here. And now this one here is repeating our first one. So we have a total of 1, 2, 3, 4, 5, 6 inflection points within one period. In fact, there are actually infinitely many inflection points, infinitely many x-intercepts, and so forth. But each one of these, if we just add the period to it, we'll get another thing of the same type. In other words, if I have this one right here for a maximum, if I add 2 pi to the x, I get another maximum corresponding to it right here. That's a corresponding part of the graph in the next part. And if I add another 2 pi, we're over here. Or if we subtract 2 pi over 3, I should have said. Add 2 pi over 3, I go to here. Add 2 pi over 3, I go to here. And add another 2 pi over 3, I'm over here. If I went here and subtracted 2 pi over 3, I'd be this one maximum right here, and so forth. So let's see if we can compute some of this. Suppose we want to find these red dots the x-intercepts, then what we're doing is we're solving the formula f of x equals 0, solving that equation. So we have 2 sine cubed of 3x minus sine squared of 3x minus 2 sine of 3x plus 1 equals 0, and we want to solve that. So we're going to start by simplifying a bit by substituting u equals sine of 3x as we did above. And so we get 2u cubed minus u squared minus 2u plus 1 equals 0. And we want to find the places where that is equal to 0, which corresponds to factoring this. Now, there is a universal cubic formula, but I doubt you've ever studied that. So one way we can do this is to graph this on our calculators, say, replacing the u by x. So 2x cubed minus x squared minus 2x plus 1. And you may have to experiment a little bit for a window, but this one seems to work okay. And it looks like right here at -1, it crosses the x-axis. It looks like it again at +1, I think, and then also maybe somewhere in here half, maybe. So we can calculate these intersection points with the x-axis by doing a calc 0 on our calculator, and this one turns out to be at -1. This one turns out to be 0.5 or half, and this one here turns out to be at 1. So if we check that in our calculator and we put in -1, positive 0.5, and positive 1 for x, sure enough we get 0 for y, and of course we could check it by hand by plugging it in there as well. So there's the roots of the numerator. X is -1, positive 1/2, and 1. Now that's x up there, which means that this factors as, of course, the leading coefficient 2 is still there, and each one of these corresponds to a linear factor here. X minus 1 corresponds to x plus 1 here. Then we get x minus 1/2 and x minus 1. Of course, x minus a -1 is x plus 1. Now we can check our factoring by plugging that version in, y2, and we see that the tables and graphs match. Now these x's here are not really our x's to begin with. These x's are our u's to begin with. So, going back to our original equation, here's our original equation. We say we want to find 2u cubed minus u squared minus 2u plus 1 equals 0, where u is sine of 3x. Or later on, I'm going to do another substitution where theta is 3x, so that's sine of theta, where theta is 3x. Now this factors as 2 times u plus 1 times u minus 1/2 times u minus 1, and that's equal to 0. Now if you multiply a bunch of things together and get 0, one of the factors has to be 0. Of course 2 is not 0, so that either means that x plus 1 is 0, or x minus 1/2 is 0, or x minus 1 is 0. And just adding the opposite to both sides here, we get u is -1, or u is 1/2, or u is 1. So we have solved for u. But of course u is something that we put in there to substitute. And of course you could have picked a different letter. But if we do that, then we need to switch back to this. So I'm going to let u be sine of theta. Remember, theta is 3x. So sine of theta is -1, or sine of theta is 1/2, or sine of theta is 1. Each one of these is a trigonometric equation, which will have infinitely many answers. Now let's see if we can figure out the appropriate things to do with this. Now let's think of sine of theta. On a unit circle picture, sine of theta is, which in this case is -1/1, can be thought of as -1/1. In a unit circle picture, that's going to be y over r. Or not necessarily a unit circle picture, but a circle, any circle centered at 1 with radius r. And so sine of the theta is y over r when you're thinking of the angle in standard position. So, remember theta is the radian measure of the angle in standard position. And so the terminal side of our angle then will meet a point with x coordinate x, y coordinate y, r coordinate r, where y over r is -1/1. So one way to do it is to choose r to equal to 1. That makes it the unit circle. Then y would be -1. So what does that mean? Well, let's see. It's a radius 1, but the y is -1. It's pointed straight down. So that says if I'm looking at this picture, remember standard position starts at 0, goes out along the x-axis, and the the terminal side is going to start right here at 0, the origin, and point straight down. So it's going through this point, 0, -1. So x is 0, y is -1, r is 1, and from that we can find sine, cosine, tangent of that angle. Furthermore, we even know what that angle is. Well, we know the possibilities for what that angle is. There are infinitely many of them. One way to get there is to rotate this way. That's the shortest rotation. That would be -π/2. Or another way is to rotate this direction in the positive direction, and the shortest rotation in the positive direction is 3π/2. Of course, we can add any multiple of 2π to that to give a full another rotation in the positive or negative direction, whether we're adding or subtracting 2π. And that gives us another angle with the same terminal side. So only one terminal side, but infinitely many rotational angles. So I'm going to choose, in this case, 3π/2 is the way to represent that, plus multiples of 2π. So here we go. Let's see, that's right here. So it's 3π/2 plus 2nπ, such that n is an element of the integers. Remember that funny looking z is the set of integers. This means is an element of, so n is an element of the integers. The vertical line is such that, and this is a set notation. So theta, not x, but theta is an element of this set, 3π/2 plus 2nπ, where n is an integer. And if you pick any theta in that, you're going to get a terminal side pointing straight down, and you're going to get a sine of that to be -1. Okay, similarly, let's do sine of theta is +1. So we're going to think of 1 as being +1 over +1 is y over r. Both y and r are 1. That means we're pointed straight up, going through the point 0, 1. Again, x is 0, and we get an angle there. Well, we could do -3π to get over 2 to get there, or we could do the shortest way, and the positive way would be just π/2. And of course, any multiple of 2nπ we could add, any multiple of 2π we could add to that, any integer multiple. So theta is an element of the set π/2 plus 2nπ, such that n is an integer. So again, one terminal side, infinitely many angles that will give you that terminal side. Now so any of these angles for theta will give us sine of theta is 1. Now what about this one in the middle? Sine of theta is 1/2. So let's see, where is that? That's right here. Sine of theta is 1/2. That's y over r. And so again, if we take the angle and measure theta radians in standard position, it's a terminal side. I'm going to think of the r as being 2. If I do that, I'm not doing it on a unit circle, but a circle of radius 2, but centered at the origin. And then the terminal side, of course, the initial side is always the positive part of the x-axis. The vertex is always at the origin for standard position. And if you do that, then the terminal side is going to meet that circle of radius 2 at the point where y is equal to +1. Okay, so let's look at the picture of that. Okay, this is a little bit bigger circle. These are the scales. So that's radius 2. And we actually don't need all of this. We need the y to be 1. So y equals 1 is this horizontal line right here. So there are actually two places, this one and this one. These down in the third and fourth quadrant have the same reference angle, but they're not legitimate. So the only ones that work, the two rotational angles, the two terminal sides that we end up with, are in the first or second quadrant, not the third or fourth quadrant. Now, what does that angle work out to be? Well, if you look at the reference triangle, we know this side is 1 because y is 1. We know the radius of the circle is 2, so that's 2. Pythagorean theorem tells us that the other side is square root of 3. And you may recognize that if you sort of reflect that over, you get a big triangle here that's 2, 2, and 2 on each side. So this bigger angle right here is 60 degrees, or pi over 3. Half of that's going to be the smaller angle here, which is pi over 6, or in other words, 30 degrees for the reference angle. So what are some rotations that will get you there? The smallest angle of rotation, which is also the smallest positive angle, would be pi over 6 to this one right here in the first quadrant, and this one in the second quadrant would be pi minus pi over 6, so that's 5 pi over 6. So, all these that give you the terminal side here in the first quadrant, the same as this one right here, would be thetas that are pi over 6 plus 2n pi, again, n is any integer. All these that give you this terminal side in the second quadrant would be theta equals 5 pi over 6 plus 2n pi, where n is an integer. So, when we put those together, there were 4 possibilities. The terminal side pointed straight up, straight down, out here in the first quadrant, out here in the second quadrant. So, what does that turn out to be? Well, it's pi over 6 plus 2n pi, pi over 2 plus 2n pi, 5 pi over 6 plus 2n pi, 3 pi over 2 plus 2n pi, any of those such that n is any integer. Now, that's what theta is. Now, but remember we did a substitution earlier that theta was 3x. So now we switch the theta back to x's. So remember what we did? We substituted a u, solved the polynomial equation for u, then substituted back in sine of theta for u, solved that trigonometric equation, and then finally we switch from thetas back to x's and we're going to solve for x. And this is what we're going to be really looking for. So if x equals pi over 6 plus 2n pi, if 3x equals that, what's x? Well, just divide both sides by 3. So pi over 6 divided by 3 is pi over 18, and this is 2 pi over 3 times n for this part. Which means that once we found that root of pi over 18, shifting by multiples of 2 pi over 3 gives us a corresponding root of the graph as we look at these things periodically. Well, earlier we'd already figured out that the period was 2 pi over 3, so this verifies that or makes sense of it too. Again, when we do the next one, divide by 3, it's the same as multiplying by a third. A half times a third, or a half divided by 3 is pi over 6. And again, we get 2 pi over 3n. Multiply this one by a third, or divide by 3, we get 5 pi over 18 plus 2 pi over 3 times n. And finally, multiply this last one by a third, the 3 cancels, you get pi over 2 plus 2 pi over 3n. And any of those x's will make f of x equal to 0. So those are the infinitely many x-intercepts. Of course, each of these is an x value, and then, of course, y is 0. So here I've listed them as ordered pairs. Technically, intercepts are actually ordered pairs, but, of course, we know the y-coordinate is 0. And here they are approximated. Now, of course, y-intercept is easy. It's a function, so you can just plug in the x to get y. And, of course, if it's on the x-axis, on the y-axis, excuse me, x equals 0. And so that's the, just plug in x equals 0. And, of course, it's a function. It's only going to have one value, which we work out here. 3 times 0 is 0. Sine of 0 is 0. And so this turns out to really just be 1 in the end. So 0, 1 is the one and only y-intercept. Now let's look at what we have so far back on the graph. So this guy right here, this first one, is the smallest of these guys right here that we found. It is the pi over 18. The next one's at pi over 6. The next one is at 5 pi over 6. Notice that pi over 6 is 3 pi over 18. So we got pi over 18, 3 pi over 18, 5 pi over 18, and 9 pi over 18 is a half. So pi, a half a pi, so it's pi over 2 there. And so those are in order the x-coordinates of those 4 red dots. So the first one again was pi over 18, I believe. Let's look back. Pi over 18, pi over 6, 5 pi over 18, and pi over 2 should be the x-coordinates of those 4 red dots where it crosses the x-axis. Those 4 red dots. Now, if we shift any of those by 2 pi over 3, we get another one. So there are 4 classes, we might say, of roots here, and we have shifts of them by any one of them by 2 pi over 3. So add 2 pi over 3 to that one, which would be, let's see, pi over 18 plus 2 pi over 3. We could get a common denominator, work that out. Whatever that is, that's going to be the x-coordinate right here, where that graph crosses the x-axis again, and it corresponds to this part of the graph where this one is. And we can do the same for the others. So in any one period, there are 4 x-intercepts, but overall, there are infinitely many falling into those 4 classes. Okay, next let's see if we can find maybe these maxima and minima here. So I'll see 1, 2, 3 minima and 3 maxima in one period. So let's see, how can we do that? Well, if you really want to do this correctly using some calculus, then what we want to do is we want to take the derivative and set the derivative equal to 0 and solve. So the derivative, again, if we do a substitution where u is sine of 3x, this is the derivative of 2u cubed minus u squared minus 2u plus 1. We know how to do polynomials pretty easy. So that's 6u to the second times the derivative of u minus 2u times the derivative of u minus 2 times the derivative of u plus 0. Now u is sine of 3x or sine of theta, so du is cosine of theta d theta, or cosine of theta times, let's see, the theta is 3x, so derivative of theta with respect to x is just 3. So du over dx is just 3 cosine theta. So notice these all have a du over dx, which I factored out front, and then I wrote that as 3 times cosine of theta. Of course, 2 times 3 is 6. So we got a 6 cosine theta out front. And inside we've got 3u squared minus u minus 1. Now, again, I can plug back in what u is. There it is. So substituting in u equals sine of 3x. Now we want to set the derivative equal to 0. So what are the possibilities? Well, 6 is a factor, but it's not 0. Cosine of theta could be 0. Or this polynomial, 3u squared minus u minus 1 is 0. Well, we'll come back to cosine of theta equals 0 in a minute. On this one here, unfortunately, it doesn't work out very nicely with like anti-FOIL factoring, so we'll have to factor or solve that using the quadratic formula. So quadratic formula says we got the opposite of b plus or minus the square root of b squared minus 4ac over 2a, where those are the corresponding coefficients. And we work this out. 2 times 3 is 6. Let's see, negative 1 squared is 1. 2 negatives make a positive, that's 12, plus 1 is 13. Well, it's 1 plus or minus square root of 13 over 6. Okay, well, that's kind of messy, but nevertheless, that's what we have. Okay, so cosine of theta is 0, or u is this. Well, u is sine of theta. So, and there's 2 possibilities, the plus and the minus. So, we either have cosine of theta is 0, or sine of theta is 1 minus the square root of 13 over 6, or sine of theta is 1 plus the square root of 13 over 6. Now, just like we did before, cosine of theta is 0. We could do, one way we could do that is with looking at a sort of our unit circle picture. Cosine is x over r. If we take r to be 1, cosine is 0 when x is 0, then it's either pointing straight up or straight down. So there's 2 different rotational angles, say pi over 2 or 3 pi over 2, plus multiples of 2 pi. Let's see, where are we? Right here. So it's pi over 2 or 3 pi over 2 plus 2n pi for theta. Now, unfortunately, there's no other way to do this other than to say an arc sine, or you could possibly do an arc cosine or arc tangent to work it out. But if we say sine of theta is this, one possibility is the arc sine or inverse sine of that. But then we can also get multiples of 2 pi. Another possibility, when you're doing sine, if you have a sine and you know a particular y value, notice that if you graph a horizontal line at that y value, it's going to intersect your unit circle at 2 places. and those two rotational angles that you're going to get are supplements of each other. So when I have this and solve for theta, one possibility is arc sine of 1 minus square root of 13 over 6. Another is pi minus arc sine of 1 minus square root of 13 over 6. And then each of those only gives you one possible answer. To get all the possible answers for theta, you're going to actually add on the period of sine, which is 2 pi times any n. So when you put all that together, okay, those are the two rotational angles that will give you sine of theta is 1 minus the square root of 13 over 6. Similarly, you're going to get two rotational angles that give you sine of theta is that. Okay, so with the plus there, so all together we get 1, 2, 3, 4, 5 within any one particular period. Period is 2 pi for theta. But now theta is 3x, so divide everything by 3. And we get pi over 2 divided by 3 is pi over 6 plus 2n pi. This is going to be pi over 2 plus, I said 2n pi, 2 pi over 3n. Because you're dividing both parts of this by 3, because you're distributing that. Here we get pi over 2 plus 2 pi over 3n. Here we get this arc sine times 1/3 plus 2 pi over 3n, and so forth. You can read that across there. The two green ones will make sine of theta 1 plus square root of 13 over 6. The two orange ones make sine of theta 1 minus square root of 13 over 6. And the red one will make cosine of theta equal to 0. Now we know basically what x is, and these we know we have exact values for everything. Some of them are fairly nice, like pi over 6, but some of them, to say exactly, you have to use an arc sine or arc cosine or arc tangent function. I used an arc sine or inverse sine function here. But we can approximate these things. Pi over 6 is approximately 0.5236, and 2 pi over 3 is about 2.0944. And pi over 2 is about 1.5708. Arc sine of 1 minus the square root of 13 over 6, and then multiplied by 1/3 is about 1.9442, and so forth. So 1, 2, 3, 4, 5, 6 places within one period that give us the first derivative is equal to 0. So there should be up to 6 extrema. Now some of these may be may make the second derivative 0 as well, so those could possibly be inflection points instead. But we have a total of 6 within one period. So let's take a look up here and see if we can see these in our picture. So we have 2 mins, 2 max, and then another min here and another max. So we have 3 minima, 3 maxima. Those are our 6 values again. And so if we did the x value of this minimum, that's the smallest one of these numbers, approximately 0.1745, or exactly pi over 18. The next one is at pi over 16, or approximately 0.5236, and that's going to be the x-coordinate of this maximum here, and so forth. You can just keep going from there. Alright, what about now finding inflection points? To do that, we need to look at the second derivative. Okay, and you can see where I did some of the approximation there on the calculator. So here's a close-up graph of just one period from 0 to 2 pi over 3. And again, we can see those places we've already identified as x-intercepts and max and min. But what about some inflection points? Okay, and here's summarizing this so far for one period, and then multiples of 2 pi over 3 will give us that. We can approximate some of these guys here. We could have done this table without finding all the derivatives by doing some 0, calc max, calc min, and so forth. Alright, here's a graph of the original function, which is the blue one, I believe. Yeah, blue. And then if you took its derivative, it's what we have in red here. So let's see if we can actually compute a formula for that. Again, after the substitution in u's, f of x is 2u cubed minus u squared minus 2u plus 1. We can do a derivative there and get 6u squared. I'm sorry, that's the first derivative. That's the first function. The original function is that. The derivative is 6 cosine of theta 3u squared minus u minus 1, or here it is all written out with x's. And so now I'm going to do another derivative of that to get the second derivative. So the 6 is a constant multiple, so I just brought that out. And I'm going to use the product rule. Cosine of theta is the first term, and then the 3u squared minus u minus 1 is the second term. Second factor, I should say. So the first term is first times derivative of the second, then you got plus the second times derivative of the first. First is cosine theta, the derivative of the second is the derivative of 3u squared minus u minus 1, which is 6u minus 1 times the derivative of the u. Plus we have the second, which is 3u squared minus u minus 1 times the derivative of the first. Derivative of cosine theta is the opposite of sine theta, d theta over dx. Be sure you watch the parentheses around the negative sine theta there so we don't interpret that as subtraction. Now, the derivative of theta, let's look up here. Remember, theta was 3x, so d theta over dx is just 3. U is sine of 3x, which is sine of theta, so cosine square theta plus sine square theta equals 1. That's a basic Pythagorean identity for trigonometry. So cosine square theta is 1 minus sine square theta. So cosine square theta is 1 minus u squared. Du over d theta is the derivative of sine theta, which is cosine theta times derivative of theta. Again, the derivative of theta is 3. So du over dx is 3 cosine theta. Now let's see if we can substitute some of that in. The du over dx is 3 cosine theta. The d theta over dx is 3. So I'm down to this line right here. Now let's see what I can do here with this. Well, first of all, that has a 3 and that has a 3. So I can bring that out front, factor it out, times the 6 there is 18. Now what's left? The 3's gone. So I've got 6u minus 1. Cosine theta is, well, here's a cosine theta times cosine theta, which is cosine square theta, which is 1 minus sine square theta, which is 1 minus u squared. So that times that becomes 1 minus u squared out of the 6u minus 1, 3 up or out front. Sine of theta is u, correct? So this is negative u times this. Now, this is just doing everything in u's. Do FOIL here. Negative u squared times 6u is negative 6u cubed. Negative u squared times negative 1 is u. 6u times 1 is 6u. Negative u squared times negative, negative u squared times negative 1 is positive u squared, that's here, and negative 1 times 1 is 1, that's there. Distribute here, we get this part. Combine like terms, we're down to here. Negative 6u cubed minus 3u cubed is negative 9u cubed, and so forth. So there it is, the decreasing terms, and I factored out the negative 1, put it out here. I didn't see anything else I could do with that in terms of factoring it out. So I just switched back to sines of thetas for sine of theta equals u. And then now substitute in finally the theta is 3x. And we have our final version of the second derivative. Now the thing we're mainly interested in is when is that second derivative equal to 0. And so we could solve this. Now that is a cubic, and again, without a cubic formula, which typically is not taught in pre-calculus, we would have to do something like putting this in the calculator and working it out. which we could have done earlier. So where are we here? So here I've graphed the original one in y1. The second one is the first derivative, I think. Okay, now let's keep going with that. So if I graph the derivative, which is right here, with this, and I could graph the second derivative, which is right here, along with that, I could look at those together. Places where the second derivative is 0 are where the first derivative has a max or min and the original function has an inflection point. So one thing I could do is just do a calc max or min on the first derivative, and that x value will be at least approximate value on the inflection point, which is about the best thing I'm going to be able to come up with here anyway. So that's what I did here with all these screens. You can take a look there. The y1 is the original function, y2 is the first derivative. Found an appropriate window for one period. Did a calc max here for the maximum on the derivative, and then that's going to be a place where we have the same x value is going to be a place where we have an inflection point here, and so forth. Find the y value of that on the original function, and that's going to give you the x and y coordinate of that inflection point. And do that all the way across here. So here we finally have the graph of the original function in blue for one period. Then red is its derivative, and green, at least what would fit on the screen here vertically, is the graph of the second derivative. And notice that where the green one crosses the x-axis, the second derivative is 0, the first derivative has a max or min, and the original function has an inflection point. Similarly, right here, we have an x-intercept of the derivative. The second derivative right here. The derivative has a maximum, and we have an inflection point there. So I've kind of identified in purple here. I think you can kind of see the inflection points. Now, of course, that's just for one period. Okay, this goes on for various periods. Here I zoomed out a little bit. You can actually see the extrema of the second derivative in this view, and you've seen at least a couple of periods. I think it's exactly 2 periods, from negative 2 pi over 3 to 2 pi over 3. Gives exactly 2 periods of all three functions, the original, the derivative, and the second derivative. So going back into 2 periods of just the original function, we see this, and in purple I've got identified the inflection points. These up here are local and global maxima. We have global and local minima down here at these green ones. And these 2 red ones, that red one right there is both a maximum, local maximum, and an x-intercept. This red one right here is a local minimum and a x-intercept. And the red ones in general are x-intercepts. And then this is again for one period. They all have shifts of that by subtract negative 2 pi or add negative 2 pi over 3 to each of those x's, keep the y's the same, and you'll get the corresponding points over here in this period. Okay, boy, that was a lot of stuff. So we kind of reviewed a lot of things there. Okay, there's your local minima, global minima, and maxima there. The range, approximately what it is there. Okay. And intercepts. So we got to review lots of cool stuff about trig functions. We know some of their basic characteristics. Solving something like this as an equation involved a substitution and working with polynomial functions first. Once we got it down to a substitution where we had sine of theta, where u equals something like this, that's sine of theta equals something. Now we're solving trig equations. We got to look at how we can see those, visualize those on a circle picture where the circle is centered at the origin, and we're looking at angles there. Find angles there, or in other words, find the solutions in one period, and then add multiples of 2 pi to get the others, but that's just for theta. Substitute back in 3x equals theta, divide everything by 3, and now we find the corresponding values for x. We had to do a similar kind of thing for the first derivative to find the extrema of the original function, and do a similar kind of thing for the second derivative to find the extrema of the first derivative and the inflection points of the original function. So that reviewed a lot of calculus, but also a lot of algebra and a lot of trigonometry. So, this is a pretty involved problem, but you should be able to do this based on your knowledge of trigonometry. It's a good example to help us kind of brush up or review or even learn several different basic things about trigonometry that are useful.